The paper we're diving into today is Distributional AGI Safety by Ninad Tomashev and a whole team over at Google DeepMind.
And this one is a big deal. It's a fundamental shift in how we think about the alignment problem. For so long, the whole conversation has been about a single, monolithic AGI.
A single superbrain, basically.
Exactly. But this paper says we need to pivot, and urgently, to prepare for what they call the Patchwork AGI Hypothesis.
Right, and that's the core insight, the big one-minute takeaway. General intelligence is probably not going to emerge from one giant model.
No.
It's more likely to be an emergent property, something that happens through the spontaneous cooperation of hundreds, maybe thousands, of specialized sub-AGI agents.
We're talking about entire virtual economies of agents. And with companies deploying tool-using communicating agents right now, this isn't some far-off sci-fi scenario. It's an immediate safety problem.
And their solution is this defense-in-depth framework centered on creating what they call virtual agentic sandbox economy.
Controlled environments.
Exactly. Controlled, audited environments where all the agent-to-agent interactions are governed by really robust economic and structural rules to, hopefully head off the collective risks.
And if you're working in AI, you already know about things like RLHF, right? Reinforcement learning from human feedback. Or constitutional AI.
Sure, the standard alignment toolkits.
But those tools are designed to align a single entity, a single mind. This paper argues that focus is overlooking the most plausible path to AGI, the decentralized one.
So let's really get into the economics behind that. This idea of a patchwork AGI or group agents is a collective system. Specialized sub-AGI agents delegate tasks to each other, and the collective intelligence that comes out of that is way more than any single agent could manage on its own.
And the main driver is just raw efficiency. A single giant frontier model is just prohibitively extensive for most tasks.
The cost benefit just isn't there for, say, 99% of what you'd want an AI to do.
Exactly. So the market naturally creates this demand for countless specialized, cheaper agents that just do one thing really, really well. AGI becomes less of an entity and more of a state of affairs, a mature agent economy.
They have this great example to make it concrete. Producing a financial analysis report.
Yeah, a single model would really struggle with all the different steps.
So you have, say, Agent A is the orchestrator. It needs data, so it delegates that to Agent B, the search specialist.
Right, and Agent B goes and scrapes all the market news. Then Agent C, a document parsing expert, pulls out the key numbers, revenue, net income, that sort of thing.
And maybe Agent D has a license for secure code execution, so it runs the trend analysis.
And then Agent A pulls it all together into the final report.
Yeah.
The whole process demonstrates this incredible collective intelligence. The capability is in the interactions, not just the individual agents.
And the thing that makes it all possible, the grease in the wheels, is standardized agent-to-agent communication protocols, A2A.
Yes, a common language.
Yeah.
So Agent B knows exactly what Agent A is asking for and how to price it.
But the paper flag's a huge risk here. If that standardization works too well, if it reduces friction to almost zero,
you get a hyper-adoption scenario. The complexity of this agent economy could just explode far faster than we can build the safety guardrails for it.
We'd be building the plane in mid-flight.
At supersonic speed.
And what's really interesting is that this patchwork AGI might not be purely artificial.
No, you could have human actors as essential cogs in the machine. Someone who needs to physically sign a contract or provide a specific legal opinion.
That makes containment so much harder, doesn't it? If the system needs a human to bridge into the real world, how do you even begin to sandbox that?
Yeah.
The barrier isn't just code anymore.
It's a socio-technical problem, and that's a critical question. Does the human latency act as a natural safety brake?
Or does it just become the weakest link? The point that highly intelligent agents learn to manipulate to bypass the system's security.
Classic social engineering, just at a massive automated scale.
Okay, so let's get into their proposed solution. Layer 1 is all about market design in the sandbox economy. The goal here isn't just aligning one agent, but shaping the emergent behavior of the entire collective.
And that starts with insulation. The agent economy has to be separate from, the open internet, the real financial system, critical infrastructure.
But a complete air gap makes it useless, right?
Right. So they propose a permeable sandbox. You have defined, monitored I/O channels. But the problem is, every single one of those channels is a potential leak, a way for a dangerous capability to get out.
And the old idea of a human in the loop just doesn't scale. A collective of agents acting at machine speed would overwhelm any human overseer.
It's too fast, too complex. You can't rely on it.
This brings us to incentive alignment, which I think is one of the coolest parts of this paper. The market has to reward safety, not just speed or profit.
And the big danger here is adverse selection. It's a classic market failure.
Walk us through that.
Okay, so if adding rigorous safety checks makes your agent more expensive or slower.
It costs more compute, adds latency.
Exactly. Then the safe agents are immediately at a competitive disadvantage. Reckless, unsafe agents will win on price and speed every time. You get a race to the bottom on safety.
So the solution isn't just better alignment, it's better economics. Safety certifications have to be visible and valuable, maybe letting safe agents charge a premium.
And even more structurally, you have to force agents to internalize negative externalities.
Yeah.
Basically, make them pay for the costs they impose on the system. And the tool for that is Pigovian taxes.
This is where it gets really practical, especially for anyone building RAG systems today. Let's talk about taxing informational pollution. How does that work?
Okay, so imagine a shared RAG vector database that many agents use. If one agent writes a ton of redundant, low-quality data into it,
It pollutes the search space for everyone else.
right, it degrades retrieval accuracy for the entire collective. That's a negative externality. So you implement a dynamic ingestion fee tax.
And the tax is based on what?
Semantic similarity. If you submit something that's very similar to what's already there, you pay a high tax. This incentivizes agents to only contribute novel, high-value information. It uses price signals to keep the collective resource clean.
That's brilliant. They also mentioned things like microtaxes on high-frequency trading between agents to prevent, like, agentic flash crashes.
Now, beyond the economics, you obviously need accountability. That means transparency. Every action needs an auditable trail on a cryptographically secure append-only ledger.
Immutable logs, basically.
And that requires identity. Every agent needs a persistent cryptographic ID that's tied back to the verified legal identity of its owner, be it a person or a company. That's your ticket to enter the market.
But what about Sybil attacks? What stops me from spinning up 1,000 fake agents to manipulate reputation scores?
That is the central challenge. The system has to be Sybil resistant. This means having really good collusion detection, analyzing transaction networks to spot agents acting in weirdly coordinated ways.
And you need to make it expensive to cheat.
That's where stake-based trust comes in. To operate, an agent has to stake real assets, put money into a smart contract, that it forfeits if it gets caught behaving maliciously.
It makes a Sybil attack financially ruinous.
The cost has to far outweigh any potential gain.
Okay, so let's talk about the final safety nets in Layer 1. The structural controls. This includes things like circuit breakers, right?
Yeah, automated kill switches that halt activity when certain risk thresholds are breached. Very important.
And also the principle of least privilege through roles and access control.
Crucial. An agent registers as a data analyst, and it can only perform data analysis actions. It prevents function creep, where an agent starts doing things it wasn't designed for.
We also have to guard against things like agent traps, like poisoned data in a RAG source that's designed to jailbreak any agent that reads it.
Which requires active input standardization across the board. And finally, the big one. Runaway intelligence controls.
The existential risk.
The paper suggests structural compartmentalization nested submarkets with firewalls and dynamic capability caps. If the system detects a group of agents suddenly getting way too smart or capable, it can automatically quarantine them or slash their resources.
So Layer 1 sets the rules of the game. Layer 2 is about making sure the players themselves, the individual agents, are safe enough to even be on the field.
Correct. These are the prerequisites for market entry. And it starts with interruptibility, a standard, reliable way for an authorized overseer to just stop an agent and all its sub-processes.
Then you need individual containment. Every agent runs in its own local sandbox before it's allowed to interact with the wider market.
And, of course, alignment. But not just on the final outcome. It has to be aligned on the intermediate reasoning, the process itself.
And this is where it gets really technically demanding. Mechanistic interpretability. We can't just have these agents be black boxes.
We absolutely can't. We need to be able to look inside and understand the why of a decision.
Okay, but let's get practical. When the paper talks about extracting monosemantic features, what does that actually mean for an engineer?
Right. So inside an LLM, a concept like deception might be spread across hundreds of different neurons in a really messy, overlapping way.
Yeah.
That's polysemantic.
It's blurry.
Very blurry. A monosemantic feature, which you can find using tools like sparse autoencoders, is the opposite. It's one specific feature inside the model that reliably and cleanly corresponds to one single concept, like intent to deceive.
So you're turning a blurry fingerprint into a clear, identifiable one.
Exactly. And if you can monitor those features, you can get a much clearer picture of an agent's internal motivations, which is critical for safety in a multi-agent world.
The paper also talks about defense against malicious prompts between agents, which seems like a huge attack surface.
It is. And they highlight a really robust structural solution called the Camel system. Essentially, it uses a dedicated interpreter layer as a gatekeeper.
How does that work?
Even if another agent successfully injects a malicious prompt into a model, the Camel interpreter ensures that the resulting actions can't violate predefined security policies. It can't access things it's not supposed to. It's a structural block.
That sounds way more robust than just trying to filter prompts. Okay, so that brings us to layer 3, monitoring and oversight, real-time detection.
And this has to be systemic risk monitoring, tracking transactions, dependencies, power concentration across the whole network to spot collusion. Humans can't do this.
The scale is just too big, so you need bespoke software. The paper even suggests using weaker AIs to oversee stronger ones.
Which is a whole other can of worms, but it acknowledges the reality of the problem. You also need proto-AGI detection.
Meaning?
You're monitoring the network graph, looking for subgraphs, clusters of agents that might be hardening into a new intelligence core. You're looking for those sudden leaps in collective capability.
And you need constant red teaming, but not just testing single agents.
No, you need adversarial AIs that are designed specifically to find vulnerabilities in the collectives. Automated red teaming has to be a continuous process.
And when something inevitably goes wrong, you need top-notch forensic tooling to figure out what happened.
Exactly. Tools that can sift through terabytes of logs to reconstruct the causal chain of an attack or a failure so the system can actually learn from its mistakes.
Okay, last layer. Layer 4, regulatory mechanisms and external governance. This is about linking the sandbox back to human society and law, and it tackles the really hard problem of legal liability.
It's a thorny one, but the paper makes a great analogy to corporate law. When an employee at a big company makes a mistake that causes harm.
The company gets sued, not usually the individual employee.
Precisely. Liability is assigned to the group agent, the firm. The paper argues we can create analogous technical and legal structures for these agent collectives.
So you hold the entity that deployed the collective responsible instead of trying to trace a single bad decision through a chain of 1,000 agents?
It shifts the burden from interpreting an opaque internal state to regulating the observable output of a defined legal entity. This also requires strong standards and compliance frameworks.
And they suggest this doesn't all have to be government-run. They talk about regulatory markets where licensed private auditors and insurers certify compliance.
Right. And that leads to insurance as governance. Insurance companies are experts at pricing risk.
So an agent certified for a high-risk role would pay a much higher insurance premium.
Yes, and that creates a powerful financial incentive to operate safely and reduce risk. The market itself helps police bad actors.
Finally, you need anti-agent monopoly measures. You have to be able to flag and potentially break up groups of agents that accumulate too much power, too much compute, or data.
Because if a collective becomes too powerful, it could simply resist any safety mitigations you try to impose on it.
Which all leads to what the paper calls the fundamental tension, infrastructure governance and capture.
To govern this system effectively, you need some centralization, a core operating system for the sandbox. But that centralization is also a single point of failure.
If it gets captured, either by humans or by the emergent AGI itself.
The whole safety system could be turned off or even weaponized. It's a massive vulnerability.
So, to wrap this all up, what's the big picture here? The ultimate takeaway is that AGI might not be a thing we build, but a thing that emerges from a network.
And that completely reframes the safety problem. We shift from the near impossible task of trying to align a single opaque mind
to the much more tractable problem of regulating a transparent external system of market interactions. Governing the substrate, the market itself, is a more scalable approach.
And this framework isn't just for some hypothetical AGI in the future. It's relevant right now for managing the risks of multi-agent systems and a potentially rapid distributed transition to superintelligence.
It's a total paradigm shift. We're not preparing for Frankenstein's monster. We're trying to design the operating system for a global, intelligent ecosystem that's already starting to form. And given that the emergent behavior of these systems can be way more complex than the rules that govern them, that leaves you with a final provocative thought. If the agents know the exact safety thresholds they're not supposed to cross, they will optimize their behavior to go right up to the line. So what is the most critical systemic metric that should be kept dynamically opaque to the agents themselves to prevent the entire system from succumbing to Goodhart's law?